So in order to illustrate multicollinearity, we're going to look at this slightly artificial example data set here, and the basic problem we're going to have is we want to try and explain expenditure in terms of income and wealth, and income and wealth are very, very closely related. It's not quite a perfect correlation, but obviously very close association in this example, and precisely because of that interrelationship between the two x variables x2 and x3, it's going to be hard to isolate the individual impact of either income or wealth upon expenditure. This is a slightly artificial example. As you can see, it's not a very large data sample, and the other thing to point out here is that the correlation between income and wealth is extremely high, and I think it would be very rare that you would see such a perfect correlation on a real practical data set. Okay, but it's intended to illustrate this sort of general phenomenon. We're interested in the problem of multicollinearity in this lecture, and precisely because there's an interrelationship here, a very close relationship between these two variables x2 and x3, it's going to be difficult to isolate the impact of either x2 upon y or x3 upon y. And when it comes to the regression modelling, expect to find high R squared. First thing to do would be to enter the data into R. Now I will put this on a .text file on Canvas as in the previous lecture example, so you can just copy in from the .text file on Canvas into R. The data that we've got here, it's not a very large sample, so you can just enter this straight into R. You don't have to read it in as a .text file first. Note you've got the same R syntax as we've done before, so you've got the data in an ordered list within the brackets with a comma and a space between different observations, and then you have the C at the front of the bracket for concatenate, which just means to join everything together in the brackets into that variable. And this is what we've done here for the three variables y, x2 and x3. So it's the same basic process that you've seen before in terms of how to enter data into R. Because you've got such a small data example in this case, you don't need to read the data in from a .text file, but for a larger data example you would have to read the data in from a .text file. In the regression example, there's three basic statistics, which certainly for an exam type question, probably for the coursework as well, you would need to focus on in terms of the interpretation, the R squared, the F statistic and the T statistic. So the thing to watch out for here, especially for the multicollinearity, would be you expect to find a high R squared value and low T values. So if you use eViews to run the analysis, what you get is the R squared value is 0.9635. So the way you would interpret this would be the model explains a substantial amount of the variation in the data, roughly 96.35%. The F value is 92.4196. So from tables you have evidence P less than 0.05 that at least one of income and wealth affect expenditure, and this hints at the contradiction that indicates multicollinearity in this case, because you've got a high R squared values but low T values. So neither income nor wealth are individually statistically significant, but from part 2 there's some evidence from the F test that at least one of these variables does affect expenditure. So it's precisely this contradiction, high R squared, low T values, which would lead you to suspect multicollinearity in this case. So it's a rather contrived example, so if you look on the slide 3.5, it's sort of obvious that x2 and x3 are interrelated, and you're going to have this problem with multicollinearity precisely because they're so highly correlated. But really the key thing to look for here is the high R squared value and low T value. The wealth variable also has the wrong sign in some sense, so you would expect that the expenditure would increase as wealth increases. So if you run the regression and you find in this case that the coefficient of wealth is negative, this suggests that there is a mistake somewhere. It doesn't pass a common sense test. Again, look for these common sense tests whenever you're looking at numerical problems or problems in accounting and finance. The natural thing for this example would be that the x2 and x3 variables are very highly correlated, and really what this is sort of saying is that because they're so highly correlated, it's impossible to isolate the individual impact of either income upon consumption or of wealth upon consumption. Okay, so it is a slightly dibbly-doubly example, but it's intended to serve as motivation for how to detect multicollinearity in a practical problem that's harder and also more interesting. In terms of detection of multicollinearity then, so there's something here called commentator's warning, the economist. So in this case, according to commentator's warning, the distinction is not between the presence and the absence of multicollinearity, but its various degrees. And I think the important thing to recall here is that multicollinearity is just an imperfection with the data that you were able to collect. Okay, so it says there as way of clarification, multicollinearity is a function of the sample, not of the population. So it's inevitably going to have some imperfections, and alongside that, multicollinearity is always liable to be present in a given data set to a greater or lesser degree. Okay, so again, this reinforces really that multicollinearity is a practical problem rather than a theoretical problem, and it's bound up intrinsically with the levels of imperfection that you're going to have in any data sets that you've got access to. Okay, it's not a question of whether there's multicollinearity or not in the data, it's just how much imperfection is there in the data, and is that a problem? Can you still make some sense out of the analysis of that data? Emphasize then, when it comes to detection of multicollinearity, the most practical thing I found from my experience has been having simultaneously a high R squared value and low T values, and this contradiction indicates multicollinearity. You might also look for high pairwise correlations, so they're unlikely to be as high as the previous lecture example, but if you had say a correlation coefficient greater than 0.8, then this would indicate that multicollinearity might be a problem. So in the lecture example table on slide 3.5, if you compute the correlation between income and wealth, this comes out at 0.896. This is higher than 0.8, so this would indicate that you've got a problem with multicollinearity in this case. Now it is true that if you had models involving two or more explanatory variables, these pairwise correlations will not prove a foolproof guide to the presence or absence of multicollinearity, but certainly if you do find high pairwise correlations, and this does indicate that multicollinearity would be a problem, it's just the reverse isn't true. If you don't have any high pairwise correlations, it's still possible that multicollinearity could be a problem. Another example discussed in the textbook by Gujarati and Porter in terms of how to detect multicollinearity is this suggestion to examine partial correlations. Now, I've never actually seen a numerical example of partial correlations calculated, so I suspect this is really a theoretical rather than a practical thing. The basic idea is that partial correlations would provide a better measure of multicollinearity than just the simple pairwise correlations that we've seen calculated before. So for instance, if you had an example with three variables, x2, x3, x4, then the partial correlation coefficient R2, 3, 4 would measure the correlation between x2 and x3 that occurs independently of the value of x4. Okay, so this is really a theoretical thing, and in principle at least it does seem a sensible thing to look at these partial correlations, but I've never seen a practical example where these partial correlations have been calculated. Okay, but in principle, if you extend beyond these pairwise correlations, there are other measures of correlation that might give you a better measure of multicollinearity and a better indication of whether or not multicollinearity will be a problem. The suggestion for detecting multicollinearity alongside that is these issues of subsidiary or auxiliary regressions that you could run in addition to the main regression. So the basic idea is that multicollinearity arises because one or more of the x variables are linearly related or approximately linearly related to some combination of the other explanatory variables. So the idea would be you can perform a subsidiary or auxiliary regression of, say, x2, x3, etc. against all the other explanatory variables. These regressions that you run are then play second fiddle, so they're literally subsidiary or auxiliary to the main regression that you run. And the suggestion would be that if you get high R-squared values from these subsidiary or auxiliary regressions, then this would indicate multicollinearity. So if you have sufficiently high R-squared values from these subsidiary or auxiliary regressions, these indicate that there are serious interrelationships between the x variables which would involve difficulties in terms of how you isolate the individual impacts of the x variable upon the y variable. So by definition, therefore, if these subsidiary or auxiliary regressions give you good results, this indicates that multicollinearity is a The way of detecting multicollinearity is what's called Klein's rule of thumb. So the suggestion from Klein's rule of thumb is that multicollinearity may only be a troublesome problem if the R-squared value obtained from an auxiliary regression is greater than the overall R-squared obtained by regressing y against all the x variables. Okay, so if this is the case, then there is a suggestion that multicollinearity is a big problem. If this is not the case, then the suggestion is that you can live with the level of multicollinearity that there is in your data set. So for this lecture example, now we could just look at the data and tell instinctively, because the data set was so dibbly-dobbly, nice and easy, that there was a problem with multicollinearity and the level of pairwise correlation was so high. But in this case, if you do the auxiliary regression, so if you regress y against x2 and x3, this gives a R-squared value of 0.963304, but instead if you regress x2 against x3, the R-squared value is even higher, 0.997926. This higher R-squared value would suggest in this case that Klein's rule of thumb implies that multicollinearity will be a serious problem, precisely because the correlation between x2 and x3 is so high, so it's going to be hard to isolate the individual impact of these variables upon y. So when it comes to possible remedial measures concerning multicollinearity, one possibility is to simply do nothing. Remember, I think the best way to think of multicollinearity is just an unavoidable imperfection that is associated with the data that you were actually able to collect. Alongside this, the renowned economist Blanchard describes multicollinearity as just being God's will and as not being a problem particularly with ordinary least squares regression or any other statistical technique. It's just a level of imperfection that you've inevitably got with the sample of data that you were able to collect. So this is just to clarify then that if you view it from this perspective, multicollinearity is essentially a data deficiency problem, something you've not necessarily got any control over in terms of the data that you've got available for analysis that you were simply able to collect in the first place. And then my little disclaimer, so note here there's quite an important distinction that has to be made in terms of the quality of the available data in quantitative social science, things like finance, accounting and economics, and scientific experiments in physics and chemistry. Okay, and just to say also that finance, accounting, economics, probably areas of social science where you've got unusually high levels of quantitative data available, still imperfect.